Alright guys, sorry for being out today, so we're going to make the best of it. I suggest you take good notes. We won't be having class tomorrow because you guys will be gone, and Wednesday is iffy because of the pre-ACT, but this is just as well as me being in your presence, talking to you. Please take notes and be ready to ask questions the next time I do actually get to see you. So the second part of chapter 2 is rational functions. Rational functions, if you don't remember, we did some last year, are basically just functions that are fractions. The denominator has got an x. As a matter of fact, there's like the definition of rational functions is something to the effect of, hey, you've got a fraction and your numerator is a function and your denominator is a function. And that is the short and sweet version. Of course, g of x can't be equal to 0 because, can't divide by 0. But other than that, we know that they can be polynomials, they can be monomials, they can be constants, right? So that's a rational function graph, or a rational function. So today and Wednesday probably, we're going to talk about the graphs specifically of rational functions because they can get a little hairy, and we're going to talk about some stuff that you probably already know and then add in some new stuff, and we're going to use our graphing calculators later and all that fun stuff. So let's just start with the first thing is you do need to know how to find the domain of a rational function by looking at the function. It's pretty darn easy. So let's just start with the first example. If I gave you f of x equals 1 over x minus 2, I don't need to know what that graph looks like. I don't need to know what that graph looks like. What I do need to know is what x values can I not use, right? Because we know that's what the domain is. So in this particular problem, we know that the domain is not the set of all real numbers because I'm not allowed to have a 0 in my denominator down here. So x would not be allowed to be equal to 2. And basically, that's what your domain is. It is all real numbers except 2. So to keep to algebra for right now, and I'll explain the calculus way to say it when I see you in person the next time. So we're going to write it in set notation. So it's the value, it's x, so that x does not equal 2. Okay, that's going to be the easiest way for us to put it right now. We could put it in interval notation. I guess I'll go ahead and show you that. I mean, I know some of you guys prefer that anyway. So it'd be everything from negative infinity to 2, not including 2, and everything above 2 to positive infinity. Again, not including 2. So that would be the interval notation way of saying, hey, I can't have 2 in the denominator because I know that's going to give me a 0. So short and sweet, to the point, if you're asked to find the domain of a reciprocal function, all you're really doing is trying to figure out where is the denominator equal to 0 at. So let's just talk about the reciprocal function in general while we have the domain. Oh, it was one of our 12 functions, right? We know it's just 1 over x. We know that if I were to graph it, and this is just meant to be a sketch of a graph because I don't want to go into a whole lot of detail here. So obviously the x-axis and the y-axis, and basically this is just the one that is it's a discontinuous function because of the fact that it's well, my brain is off. It has asymptotes. There we go. That's the word I was looking for. So like you have a piece in the positive quadrant 1, and then you have a piece in the negative quadrant 3. There we go. Actually, that doesn't look half bad. Very neat. So that's what the sketch of the graph looks like, right? Things you need to know. Obviously, we already know the domain is everything except for 0 in this case, right? Because this is the parent function. All right, this is the parent function. So I know the domain is, again, it's everything except 0. And the same thing for the range. We can see here by our graph that the range also uses all of the values except 0 because, again, there's an asymptote there. So the set of y, so that y cannot equal 0. And we're going to look at a limit way to say that more properly now that we're in big kid math. Again, it's discontinuous, right? We can see obviously it's in two different pieces. Discontinuous. There we go. I have to pick my pencil up to be able to draw both pieces. It is not bounded, obviously, because it keeps going in both directions. It has origin symmetry. I know we haven't really talked about symmetry a lot, but whenever I have the graph, that just means that I can, let me see if I can get this line to go pretty. If I graph it along, if I were to fold it over that line right there, that line is wrong. Let me try that again, but prettier. There we go, that's more accurate. So I can fold it over that line and it's symmetrical. That's what origin symmetry means. It's pretty straightforward, nothing fancy. And again, we can see that there are asymptotes, right? We know that there's an asymptote on our x-axis. We also know there's an asymptote on our y-axis. So all rational functions, well, let me rephrase that. All rational functions are going to have an asymptote of some sort. This particular one, the parent function, does have two asymptotes, vertical and horizontal. The end behavior. So let's talk about the end behavior real quick. We haven't talked about end behavior in a minute. I can see that obviously on the left side, it's not going up, it's not going down. It's pretty much flattening out at 0. And the same thing on the right side. I can see on the right side, again, it's not going up, it's not going down. It's flattening out to 0. It's approaching 0 on both of those sides. So we know that on the left side, it goes to 0, and on the right side, it goes to 0. It's not going up or down on the left or the right. It does in the middle, but that wouldn't be in behavior. So those are just a couple of things I wanted to mention, just as a reminder of exactly what a rational function looks like, just like baby stuff. So let's talk about the transformations real quick. So transformation, of course, is where we start adding and subtracting and multiplying, right? And it's the left and right and up and down and stretches and compresses and all of that stuff. So if I gave you something, transformations, to the effect of, let's just do an easy one first. G of x equals 2 over x plus 3. And I said, okay, from the parent function, what's going on here? Well, if you're really particular, you may go, okay, well, that just means that's the same thing as 2 times 1 over x plus 3. Some people will choose to do that because then you can see, okay, I'm multiplying this rational function times 2, so I know this is going to be a vertical stretch for sure. So it's going to get skinnier vertically. I also see that I am adding and subtracting a number inside parentheses, right? It's in a grouping symbol. It's in the bottom of my fraction. So that means that's a left and right movement. That's a horizontal shift. So I can see here that this graph is going to move to the left 3. It's going to move to the left 3. Okay, so to do that, you need to be able to do that. You need to be able to look at the equation and be like, this is what's going on as far as transformations go. Because in a little bit, not today, but in a little bit, we're going to be able to sketch this without using our graphing utility. Now, here's the thing. What if I gave you one that had, I don't know, let's do, f of x equals, 3x minus 7 over x minus 2. Okay, so I have a problem. My problem is the numerator is no longer just a number, and I can go, oh, look, it's 2 times bigger. So here's the easiest way to do these, and please remember that you love me. You're going to divide. Now, not synthetically divide. Honestly, long division is the easiest way here. So I'm going to divide these so that I can rewrite it in a more useful form. So I know that x will go into 3x 3 times, right? As a matter of fact, that whole thing is going to go. So remember, when you're doing long division, you're just looking at how many times will this term go into this term. Okay, not the constants, just your leading terms. Of course, 3 times, because 3 times x is 3x, right? So I'm going to multiply 3 times x is 3x. And then 3 times minus 2. I'm basically just doing the distributive property. And if you don't remember, whenever you long divide, I do have to subtract every term. So I'm going to subtract that one and subtract that one, which actually would make it a positive. These two are 0, which is what I wanted to happen, and that is -1. So what this means is that if I wanted to rewrite this, is that it obviously went into it 3 times, right? It went into it 3 times, and we had a remainder of -1. And we know, because we did synthetic division a whole lot this first part of the chapter, I would write that as -1 over what I divided by, in this case, x minus 2. Now, the reason why we like to write it like this, and I'm actually going to rewrite it one more time, is because now I can see, oh, hey, I'm subtracting on the bottom, and I've got a number that I'm adding or subtracting to the whole function. And it's easier to see whenever I want to explain a transformation. Okay, so I'm going to, again, rewrite it one more time just to make it super nice. This is a positive 3, right? So I'm going to rewrite this as -1 over x minus 2 plus 3, right? This is the same thing as this. I just put the 3 in the back and moved the negative to the top of the fraction. Just moved it around. So now I can look at this graph and go, ooh, okay, I can see a few things happening here. For example, I say that this is a negative. So that means this is going to be a reflection. Right? We know that it's going to reflect over the axis. I can also see, again, here in the denominator, in my grouping, it is a -2, so this graph is going to move to the right 2. And right here, I'm adding a 3 to the whole function. I'm adding it to that rational function. Oop, I meant to write 2 and I didn't. So I can see that this graph is also going up 3. I can tell all of that by looking at that rather than the original form, this, which obviously wasn't very helpful. So if it's nice and pretty and your numerator is just a constant, not a whole lot we have to do, just remembering our rules for transformations. If, however, I have an actual polynomial in the numerator and I want to write it in a transformed form, I'm going to have to do a little bit of division. Okay, so make sure and write that one down and ask questions if you need to ask questions. Okay, so I think I'm going to stop there for now, honestly, because the rest of it's, hey, let's graph the crap out of this. And so in order to be able to do that, I would really like to be with you in person. So I'm just going to write down a couple more. I just had my post-it note there, and I just lost it. There they are. Of the last one that I just did, and I would really like for you to try them. Because honestly, like, we know this first part, right? We know about the domain. We talked about that last year. We know the basic stuff. I just needed to remind you of that. You guys are a smart class. But the transformation thing, like, this is new. We've not tackled this yet. And not that it's difficult, but as we all know, math sometimes takes a little practice. So I'm just going to write down a couple problems, and it would just be an amazing thing if you had these completed the next time I saw you so that we could talk about them. Okay, so I'm just going to write down 3. Okay, so the first one, I would like for you to do f of x equals -2 over x plus 5. So again, tell me what's going on in this problem. Is it being reflected? Is it going to move left or right, up or down? Is it going to be stretched or compressed? What's going on in this problem? Number 2, let's do f of x equals 3x minus 2 over x minus 1. And then finally, I want you to try this one. F of x equals 5 minus 2x over x plus 4. Didn't get too crazy, but please try those out because we need to know how to do them for the next thing we're doing. And you guys have a lovely rest of your Monday. Have fun at the college fair tomorrow, and please behave.